So this presentation is multi-language data acquisition conversational agent. So we're going to look into a variety of elements of that, like how we recommend data sets, how we do introspection queries, and some other parts. I'm not going to recite the abstract because the diagrams I'm going to show, we're going to go through that abstract. A little bit about me. I studied applied mathematics. I worked at Wolf Firm Research for like 7 years, and I currently brand myself as a senior data scientist. So here's the problem formulation for the data acquisition conversational agent. These formulations are too generic probably to be useful, but I'm going to go through them. So we want to make a software system that manages the data storage, data resources, and related software resources, and provides common services for computer programs to find and retrieve and prepare or data wrangle the data sets we have. The conversational agent prompts and supports and guides the users to utilize this data acquisition system. So there are several simplifications. We're interested in tabular data sets or listing associations of tabular data. And as a first go, single line interpreters are fine. So although I say conversational agent, just having single line interpreters are fine, a big simplification is the target audience. So these are data scientists, data analysts, or people who do scientific computing, like say epidemiology or air pollution. The target audience is professionals and wannabes, full-time, part-time, but these are people who actually more or less know what they're doing when it comes to data. They have technological thinking. All right, so this is the ideal end result, one of the possible ideal end results actually, but in my opinion right now, this is the ideal end result using a command line interface to this kind of system. So you can see I just, this is the shell cell in Mathematica notebooks. So imagine I can do this on my Unix shell or whatever shell I have, right? I'm saying get a sample of 3000 JSON commodity files from AWS, parse them into long form data frame, make a data package for them, and open a notebook with that data package. All right, so then this is the translation. It has been translated, or from natural language has been something actionable has been produced, actionable code has been produced, and I have additional commands like data acquire, data wrangle, make notebook, which kind of correspond to this. An alternative, I'm going to go through these steps here, and I wrote them down, but I'm going to spell them out. So there's an alternative flow of that command, previous command line. It's more or less exactly the same. It's just the interpretation is different. So in the previous one, I was having translate, right? This here is interpret. It basically translate, interprets what's going on. So it makes some execution. This the commands are the same, right? So we're getting again JSON files from AWS. We parse them, we transform into long forms, we make data packages, open notebooks. So there's several questions here to be looked into when we have this command. Sorry, let me position this better. So yeah, where exactly we get this data, right? Like how we access the data, the warehouse, and yeah, like what are there probably should be some credentials for the users to be required. The other is that this might be a little bit too generic. Get the JSON files for 3000 electronic goods, like it's in alignment with what I wrote here. But yeah, I mean, how we actually really figure out which data sets the person has in mind, right? After that, we're going to be utilizing some software resources, like say packages for parsing JSON files, or specifically for parsing JSON files of commodity files at that particular company or location. And then we do some transformations, which is a typical data science wrangling. This is something I was presenting about last year. You can see my recording on that about the data wrangling conversational agent. So after we do that, we can put it on in the random access memory of the machine we're processing this. This can be our computer or something else, wherever this is executed. After that, we make a package, put it in the cloud, and then we open a notebook which probably uses this package. So in order to facilitate some of the parts here, right, I need to have some recommendation system. And I wrote here to be an actions recommender. It can be, you can call it anything, but it's basically figuring out from previous activities, user activities, and given the available data, right, and the input here, what exactly is supposed to happen. These two modules here, their functionalities are the same. One of them is using grammars, the other one is using natural language processing through neural networks, like say find textual answer, which is in Mathematica. All right, so when we design this kind of system, it's a very good idea to gather not just 6, but a fairly sizable list of commands and possible dialogues. Here are some examples, and I'm not going to recite them all, but the first one, recommend customer service data that has product descriptions. That's basic, right? I can rephrase it, recommend anatomical data for, say, or recommend anatomical data for males older than 30 years old, and so forth, right? We can have some introspection queries. Like, for example, here, this is not an introspection query, but this is a data quality verification query. Verify the quality of the database DBJ99. What fraction of the records have missing data? What are the distributions of the numerical columns? These are the type of things we want to do. And so this here, this one way to think about the system is to have this kind of components, right? In which, say, the practitioner having some ideas about data analysis, data wrangling, and whatever, right? They interact with the system. They, I mean, I have put Alexa here, but it can be anything, right? So there's a module dispatcher. There's a disambiguification service, right? Which figures out which of the different facets, different modules of this system should be utilized to handle the requests. And you can see some of the connections here, like say keeping logging of the data or inventory management, recipes in the perspective of preparing data, right? They correspond to the things I was already describing, both in dialogues and retrieval of data. We have a recommendation system. I'm going to again explain more about the recommendation system, and that's actually interesting. I haven't exactly done it or worked on it, but like what I'm showing right now and what I'm going to be showing in this presentation is more like a command line type of interactivity, right? Finite state machine. This here, it's this kind of real-time assistance, right? What I do right now, what should I type in right now in order to get this, always the button for this submission of that thing, making this kind of conversation. This is like not in the minimal viable product line, but it's a good idea to keep in mind. I have several other conversational agents I'm designing, which have very similar structure. This is for cooking and preparation. You can see direct analogy with data acquisition, and also for recruiting, right? So now here the inventories and the resumes and scheduling of meetings is more important. But yeah, I mean, it's pretty much the design is the same. All right, so I would like to emphasize again, this is a multi-language system, right? From both perspectives of, if I can resize this, and I guess it cannot, both from the perspectives of the input of the language and the programming languages and packages to which this is the code is being produced. And you can see I have put some of the more famous data wrangling packages. R itself, of course, it's a data wrangling language. This interpreter, it can be made in basically in anything. Right now, I'm doing this in Raku. In this presentation, I'm going to show both Wolfram language and Raku manipulation. This is from last year, but my statement that it's multi-language. It should be should be kind of seen here, right? So I have this sequence of 4 commands, like use data frame Star Wars, rename homeworld with as HU and H as HOLD, and then group by species, show counts. You can see this has been translated into different programming languages and packages in them. So also, of course, I can translate it to, if I can do this to a programming language, I can also do it, of course, to a natural language. All right, so this is from last year, just a reminder. You can see the video. A little bit more to discuss for what I'm going to demonstrate, a little bit of a framework or breakdown of general breakdown of conversational agents. This is not the only way to look at them. And this is very operational in some sense. And some people might disagree with this breakdown. Nevertheless, I know I can work with it. So at the bottom, we start with deterministic grammar rules like single line commands and finite state machines. Then the finite state machines, everyone has experienced a finite state machine. If you have been paying in parking lots, or if you have been using vending machines, if you've been using finite state machines. So the transition between the finite state machines, the states of the machines can be dynamically determined, dynamically concluded. And so one axis in making more and more advanced conversational agent is to kind of advance the front of the finite state machines and learning from previous experiences and so forth. Alternatively, we can use just better grammar parsing, right? So quite a lot of the research is kind of going in this direction. I mean, obviously they're doing both, but some people say, why use grammars at all, right? Why not just do, say, GPT-3, whatever, some kind of neural network kind of recognition? Yeah, it's possible. No, it's not that good. So this here, it's absolutely generic system, but I would like to mention that more or less this is the framework which is being used. I'm basically saying, look, I have some natural language understanding, I have some way to manage dialogues, and this dialogue management, it does actually look into previous conversations or states or previously things done and whatever kind of else I have connected. I don't deal with the speech synthesis and speech to text. This is something I assume it has been done by other systems, right? So this is actually why you see here, like plugging in Alexa here. So this is just, again, personally, how I do prefer to deal with computational conversational agents. We know what is the computational part. We get familiar with the problem domain, like say epidemiology or classification. And we make a monad for that. And then we have another monad, which doesn't need to be spelled out, but that comes from the natural language. Then we make a single line interpreter, and then we use a finite state machine, and we make a full-blown conversational agent. All right, so finally, what is the finite state machine, right? So this here is hopefully this is a live demonstration. So this a finite state machine in which you can see I'm starting, this is my start state. I'm waiting for a request. Certain inputs are going to treat in some particular way. And I apologize, this is a little bit of a cluttered type of diagram, but yeah, you can see, for example, there's a question for list prioritization. We get a prioritized list. If we get a filtering command or we get some other command, right? We go to this wait for filter to show some results, and then wait for filter can actually go with this list of item state, which because we're doing data acquisition, I'm trying to narrow down on one particular data set, right? And so if I have multiple lists, so this here, many items, this state says I have too many items, get more filtering. And if there's a unique item, this state list of items is going to go to acquire item. The item meaning the data acquisition itself, the item is going to be acquired, and then we're going back to get a request. So here, this is what is happening, right? This state machine execution, let me actually execute it. So while it's executing, I'll be talking about the command. So we have here, get a data set from statistics. I get multiple data sets, as you can see. And this actually produced a notebook here. So yeah, so this this gets multiple data sets, and I'm saying the one with 31 rows, and there are like 2 or 3 with 31 rows, and then I'm saying the second one, right, which is the black cherry trees, and then because it's a unique item, I go to this acquire item state. The acquire item, you can see here in the logs, is saying I assigned this data to object, just to this object, right? And I also created a resource notebook, right, with this location and etc., right, in which you can actually say evaluate and have some, I mean, obviously this is very rudimentary, but imagine you actually have a full-blown description of the columns, of the meaning and etc. of this notebook. It's just I haven't done this yet, right? All right, so this was the finite state machine. It should be pretty clear. I would like to mention some other parts here further with the design. It has been a challenge to figure out how to approach this system from multiple fronts. And one of the ways is I do need to think about data sources. I do need to think about what is the specification of the data, what kind of data formats we are going to be dealing with, and etc. Right now, I mean, I'm dealing mostly with tabular data, but I mean, other data can be utilized. And it is very important when I get this kind of functionalities to in this free language specifications to understand what parts of the commands say entities, like say metadata types, and what parts are like actual names of databases or some named data sets and etc. There's an interesting question of discovery, and I'm going to go to this other mind map. Like we might want to be able to discover possible connections and internal joins between the data sets we have. Like I might be very interested to produce some kind of join between my whatever electronics data set and the customer demographics, for example, all the locations of the stores and etc. So these are all different things we need to think about. And so yeah, this mind maps presumably would help go through that. I'm going to be using this mind map from now on for to the end of the presentation. The data quality part is very important, but I only tangentially discuss it. I'm not discussing network engagement and introspection queries a little bit. So random data generation, I'm a big fan. I mean, you can see just how big this is. And before going to random data generation, I'm going to mention that I'm using this principle, but the cloths have no emperor. So it's not emperor have no clothes, it's clothes have no emperor. I'm trying to make this system as ignorant about the data sets as possible. For example, the actual parse and interpret, it's something you don't necessarily see. The interface right now for what I was showing is the actual notebook, right? And then they don't live where this data lives, right? Or where the recommenders for the actual preparation recipes or actual data acquisition live. So this can be deployed and utilized in some kind of minimal software architecture, hardware-wise minimal, and I can have some kind of some kind of private cloud or some kind of warehouse, in certain basement or whatever, right? In which I have this data sets, or AWS or Google Cloud. So this is an important principle. It's also from security perspective and, to be how we're dealing with this. So random data generation, it is actually, it's like, this is the first branch here in that mind map. So you can see how I have generated with this random, with this command, right? I'm saying generate random data sets with 10 rows and 3 columns, and more or less generated. Also saying don't have more than 20 values. And, presumably if we count here, there will be less than 20. So generating random datasets, it's extremely important for testing this kind of systems. And so you can see here there's some other ways of using of parsing results, right? So this is actually interesting. This is this using neural networks, right? And so it's like there's some kind of progress bar here which you don't see. But ideally, right now this is thinking and it's going to produce some code. And yeah, it produced the code. So you can see this is the call to this function. And now if I put release hold, it's going to produce, you know, this random data sets. Of course, you know, if I use systems like this is much faster to generate, right, using grammars instead of using NLP type of this particular function concretize uses find textual answer. All right, so metadata. So some people follow, and there's some big investment from big companies about different kinds of metadata. We can, and I'm going to go to the next slide. Like you can see this hierarchical structures between different kinds of metadata. Like say, if you have a thing and that thing is a person, that person can be a patient, right? And if you have a financial product, it can be an investment or deposit and whatnot, right? So this is actually good because we want to be able to recognize, to have an entity recognition in these commands, right? In order to figure out what exactly has been asked. So this here, again, this using Raku, you can see how I'm trying to parse an entity here. And because I misspelled it, I'm being prompted that this is probably misspelled and so forth, right? So you can see this context-free grammar basically realized, okay, well, it's this thing, and this thing has you know, one word and second word, and basically this is it. All right, so what we do with others, right? So you can see this execution here produced some other it parses all these entities I have specified. It also interprets them into a particular form, right? And so because I set here UL entity dash entity, right? The UL entity, if I say something like Titanic, is going to recognize it as something where it's in the example data set. The others there, this bike store, numerical, and star schema, they come from the hierarchy I was showing here, right? So they're like a standard entity names. So again, you know, it's being able to recognize the entities and being able to put them in the correct, to recognize where they go or what it is. It's an important feature. So making recommenders is something that it can be done in several ways. And since we're usually the number of data sets in a particular company, it's not that large. I mean, Wolfram Research might be dealing with thousands of data sets, but in some usual companies, the data sets are relatively small. So because of this, if you have, maybe you don't need a recommender, but nevertheless, you know, if we can make a recommender, we can, I'm using sparse linear algebra to deal with this. From Mathematica, you can actually try out these recommenders here in this shiny interface, right? And so, not this shiny interface, a different one, I apologize. So while is this loading, I'm going to move on. Yeah, I meant this interface here. So anyway, in that interface, for example, basically you can ask for different types of data sets, right? Or you can make some requests both by metadata and by free text. Ideally, you don't need to deal with this. The conversational agent, like the finite state machine I was showing, should be able to handle this. Let me see, is this coming around? So, okay, I guess, you know, I'm going to, right now this is spinning a new server, and that's why it's kind of a little bit slow. If I take something like, say, L-line, I have these data sets, right? I use some scientist is maintaining a large database of quite a lot of data sets used in universities, right? And so basically this interface has both mathematical data sets and our data sets. So recommender systems definitely need to have a recommender system. The introspection commands, it seems pretty obvious, but for example, being able to answer this kind of questions, right? Like how many times I acquired anatomical structure last year or whatever, right? Or like how many times I dealt with, say, pathological data, or what is the last data set I worked on? I might have forgotten for whatever reasons, right? So this kind of introspection queries. There's an interesting question, or two questions. What we do with very large data sets, right? And can we do automatic discovery of interrelationships between data sets? And so, well, yeah, I mean, we start small, right? We make a system for what works with small data sets and can produce notebooks like the ones I was showing here, in which the data can be in the notebook and explained, and etc. But instead of this being the actual data set being here, imagine that there is actually a link or whatever, right? And so I'm hearing from the opening keynote by Stephen Wolfram, I did hear that, for example, there's a resource cloud object coming in or something like that, right? So it's in that regard. So then the question is, when we do that, what kind of samples we keep in this data package? When I say data package, I mean something like this, right? It can, these notebooks here from the Wolfram function repository, they can be thought as approximation of data packages. So in these data packages, I do have some way to access the data, and I also have some unit tests which guarantee certain qualities of that data. In this particular notebook, I didn't generate the tests here, but that would be actually an extremely important part of, from my perspective, about this type of notebook generation or data package generation, to have the unit tests which correspond to the filtering commands I used in order to find out or specify the data here. All right, there's another question about opportunistic joins, and that's actually a very lengthy kind of thing. But what is happening is basically I have generated a bunch of random data sets, and I found certain connections between these random data sets between the columns, looking into by using, say, fine distribution and doing some distribution tests. So I can make some additional statements here, but I do actually want to go to the conclusion. And yeah, so this is a different breakdown of the conversational agent. We discussed parts of the data, recommenders. We also discussed how the search of the data is being done, so how data wrangling is being done. Basically, I explained that last year. Generating environments, data packages, notebooks, accessing of credentials, and having a command line design. I would like to thank Kuba Putkalitsky and Diego Zvjovic. It's essential for book generation and creation, for converting of Wolfram notebooks to Markdown. And with Diego, I discussed quite a lot about data acquisition workflows and ZeroIMQ. ZeroIMQ is the way I connect Mathematica to Raccoon. Now I can answer questions. The wide form, I'll go in reverse order. So long form and wide form, it's kind of like probably it should be fairly self-explanatory if you see it. Is basically, yeah, just a moment. Yeah, so when I generate this data sets, right, they don't necessarily come in long form. This is a wide form. But now from this wide form, right, from this free column data sets, if we look into the long forms, the different variables and values are being being separated. The advantage of doing this is that then the metadata, the column names, you can treat them as data, I see another comment here. Natural language is easier for less sophisticated users than computational language, but it's a common unsophisticated users to be ambiguous and plainly wrong what to ask for. The systems should typically ask the user for natural language system. Here is what I think you want. Is that right? Correct. It's exactly that. That's why I say I'm using grammars and I'm using finite state machines. I'm not using NLP stochastic methods. That's a little bit both myopic and doomed in many ways. You just cannot trust that much. With using grammars, using stochastic parsing, and using finite state machines, I can do exactly this. So when I'm in different states, I have additional context and knowledge what exactly is happening. I can try to parse things using say standard parsers which I have, right? And then if I don't succeed, I can try to parse it with more powerful parsers. And if I don't succeed, I might try to say stochastic parsing and etc. Right? This is actually, I didn't have time to discuss it, but there are like say three. Let me see. Yeah, there are like three different types of grammars, right? I'm using native Wolfram language grammar. I'm using Karaku grammars, and then I'm using this. This NLP stochastic kind of elements. All right, I think I passed the time of my presentation, answer the questions.
Thanks, Anton. If anybody, we'll give a couple more seconds here. If anybody has any more questions, put in the chat. Otherwise, we'll end it there.
All right, thank you for your attention. David, thank you for the interesting question.